Now I'll talk about chi-square analysis of multiple variables. You'll notice this is called part 5.5 because I've inserted this between parts 5 and 6. In the past, this material has been included in the next section, hypothesis tests of association. And in a sense, all of these tests can be considered tests of association or tests of differences. I've come to think about chi-square tests more clearly as tests of differences in distribution. So the chi-square test, as I say, is normally called a test of association, but I'm proposing that we think of it as a test of the difference in distributions. It tests the relationship between two categorical variables, usually representing nominal measurement, such as sex or size preference or location, state, for example. The data are presented as contingency tables, and the hypothesis is that the distribution of one variable across categories is contingent upon a second variable. And to analyze these data, we use the chi-square statistic. We've seen this before. Chi-square is calculated as the sum of the observed frequency minus the expected frequency, that quantity squared, divided by the expected frequency for that cell. Now the difference here in a bivariate is you've got not only two or more columns, but you've got two or more rows. So the expected frequency is defined as the expected value in a cell, and that is given as the row total times the column total divided by n, the total number in the sample. So that row total is referred to as a marginal, so it's the row marginal times the column marginal divided by the total n. And you should see this as the percentage of n that's in the row times the percentage of n that's in the marginal. And that's what you would expect to see in that if the entire sample is distributed appropriately. That's what you would expect to see in each cell. This chi-square is distributed over r minus 1 times c minus 1 degrees of freedom. So the number of rows minus 1 times the number of columns minus 1. Can illustrate this sticking with our wine drinking situation. We can look at 100 wine drinkers and now a categorical variable, the measure of situation in which one is most likely to drink wine, with 5 options: with meals alone, just to drink alone, with meals with other people, just to drink with other people, or just special occasions. And a univariate analysis would test the hypothesis that the most likely wine drinking situations are distributed equally. Or, alternatively, if we think of this as differences, we could test the hypothesis that they're distributed unequally. Now we can frame this as a bivariate question by adding another variable. Let's add sex of the drinker. So sex and wine drinking situation, 100 wine drinkers again. And we add the other question: indicate your sex, male or female. Situation in which you're most likely to drink wine is the same question. And we're going to test the hypothesis that the distribution of most likely wine drinking situation is contingent upon sex. So in other words, we think that the distribution of most likely wine drinking situation probably differs from expected, but it is different for males than it is for females. One more drinking example. Now we'll look at beer drinkers and use rate by sex. So use rate is a typical measure, and marketers often segment their markets into heavy users and light users. So we need to define what a heavy user is. Heavy users purchase 6+ beers per week. So light users would be anything less than 6. And this might be screened to include only people who do drink some beer. And you should see this as a case where we've taken an interval measure, how many beers per week, and converted it into a categorical level of measurement, heavy and light. So our sample is 100 beer drinkers. You can see the data presented here. We've got columns, heavy and light, and we've got rows, male and female. And for the male, we observe 25 heavy drinkers and 25 light drinkers. But for females, we observe 12 heavy and 38 light. Now, the expected frequency is, again, the row marginal for males is 50 times the column marginal for heavy, and there are 37 heavy drinkers. So 50 times 37 divided by 100, and that gives us 18.5. So that if there were no difference between these groups, we would expect 18.5 males to be heavy drinkers, and also 18.5 females. And those two entries will be the same because the marginal for males and females is equal, 50-50. And for light drinkers, we would expect 50 times 63 for males, 31.5, and the same 50 times 63, 31.5 for females. So we can compute the chi-squared by, and I didn't include this in the table, subtracting the expected 18.5 from the observed 25 gives you 6.5, squaring it and dividing it by 18.5. Doing that for all 4 cells, adding them up, we get a chi-square value observed of 7.24. If we look up the table values of chi-square, we see the critical value with 1 degree of freedom, and notice that's r minus 1 times c minus 1. 2 rows minus 1 is 1. 2 columns minus 1 is 1. 1 degree of freedom, table value is 3.84. And because the observed statistic exceeds the table critical statistic, our conclusion is that these two variables have different distributions. Or another way of thinking of it is that they are associated. So knowing the value of one of the variables helps us determine the value of the other variables. And we can look at the data now and interpret that significant statistic, because we can see that for males, if one is a male, one is more likely to be a heavy drinker, and if one is a female, one is more likely to be a light drinker. The obverse is true as well. If one is a light drinker, one is more likely to be a female, and if one is a heavy drinker, one is more likely to be a male.